Okay, I'm going to present a work called An Efficient Steady Transient Friction Modeling for Liquid Filled Pipe Flows. My name is Douglas Monteiro Andrade. I'm from the graduate program of mechanical engineering at Universidade Federal Fluminense. This work is co-authored by Felipe Bastos de Freitas Rachid from the same university. He is a professor of the Laboratory of Theoretical and Applied Mechanics at this university. So it's really good to start a presentation, just find the work. So fluid transients are generated by abnormal and current daily operations in pipelines, but they just not happens. Pressure loads generated by this phenomenon are really greater than the steady flow regime. For that reason, transient flows, a solid knowledge of fluid transients are important for the design of pipelines. Here is a figure. In this figure, we find the power of destruction of this phenomenon. The onset of this tragedy was a transient flow, an uncontrolled transient flow. This is a picture from the Russian hydropower plant. That's it. Yeah, so uh, uh, then historically, the analysis of the fluid transits was made by applying the quasi-steady friction. What that means? That means that the modelers used the same friction equation applied in fluid developed flows. However, as you can see here in this picture, the comparison with the experimental data of Dankovs and Lewandowski, this analysis generates overestimated pressure response, and the phase is not also captured by the modeling. And the explanation for that is that the equation of fully developed flows are based in average velocity that does not capture the distinguished velocity profiles that we found in the transient. As you can see in the next slide, observe that high gradients of velocity are found during the transit. And so if you use the average velocity of the flow, just that in the fully developed equation of transient friction, you can find, you can't capture this behavior. And that's why those responses of the experimental data in the quasi-steady friction are really different. So to overcome this this limit of using the quasi-steady equation, researchers propose a different approach to capture this local and two-dimensional effect of the velocity profiles of the flow during the transient. So there is basically two different approaches regarding the coordinate. The number of spatial coordinates is one-dimensional and two-dimensional approach. Each approach has advantages and disadvantages. One-dimensional, the main advantage is the low computational cost and easy computational implementation in practice. However, it does not see the internal structure of the flow, velocity profiles, and shear discharge profiles that are really important for some hydraulic applications. In some approach doesn't seem to obey the second law of thermodynamics. In the two-dimensional, it does see the internal structure of the flow, obey the second law of thermodynamics. However, there is a huge computational cost, and it's hard. There is a hard computational implementation in practice. And here it goes, the main goal of this work, that is propose a thermodynamic consistent model that gathers the advantages of both modeling. In other words, easy implementation and still one-dimensional, but can see the internal structure of the flow and obey the second law of thermodynamics. And how we will do that with the use of the continual theory of mixtures. So let's start. The standard phenomenon is fluid flow inside a compliant pipe. The pipe is assumed to be thin-walled, slender, and the behavior of the pipe is elastic in the small deformation range. And the fluid actually in this kind of modeling is assumed to be a mixture, a structure mixture formed by shell-shaped constituents, as you can see in this picture. So indirectly, the velocity profile of the flow is captured, then the friction that is actually happening during the transient is captured. The governing equations of the model are the mass balance for the mixture as a whole, the momentum balance for the mixture as a whole, the momentum balance for each constituent that is required for a well-posed problem when you use the mixture, and that is exactly where this equation is exactly where the velocity profiles are captured of the flow. And as we are also seeing the thermodynamic consistency of the model, we also postulate the second law of thermodynamics for the each constituent and for the mixture as a whole. And there is also appear here interaction forces, AJ and MJ, that I will explain in the next slide. AJ represents the friction force that happens between the fluid flow in the pipe. Meanwhile, MJ represents the interaction force between the internal constituents, as you can see in this peak. The constitutive equations are developed obeying the objective principle in the kinematic aspects of the mixture, that the constituents can slide each other in the direction of the pipe center line. And here it goes, the second law of thermodynamics, applying those constitutive equations. As you can see here, it's highlighted in red and orange, yellow, that there is material constant that must be found. And we found those material constants applying a fully developed velocity profile plus the incompressible momentum balances for the each constituent. This set provides a linear system that can be solved, whose actually the unknown are exactly the material constants of the model. And in fact, here it goes the material constants of the model, and as they are positive, the model is thermodynamically consistent, as you can see in this slide here. If the material constants of the model are positive, the model obeys the second law of thermodynamics. So the numerical methodology, as the governing equation forms a quasi-linear hyperbolic system, we apply the method of characteristics to transform this partial differential system of equations into an ordinary system of differential equations, and then we integrate the systems along the characteristics as represented here in this figure. So we wanted to turn this model efficient computationally. So we will do in the following an analysis of the distribution of the constituents, a number of constituents. And this strategy is basically, we will see the responses of for mean pressure, mean velocity, velocity profile of two different mesh, one uniform with 5, 10, 40, and 80 constituents. Uniform, I mean, same thickness. Our constituents has the same thickness. And mesh 2, that is non-uniform. In this mesh 2 will be formed by 5 constituents in the inner regions of the flow that are thicker, in finer constituents, finer 5 constituents in a region more close to the wall. Why we do that? Because as you saw in the small video that I presented, there is a rising of high velocity gradients next to the wall. So it seems that that is the most important region of the phenomenon. As you can see here, as you increase, here there is the pressure response and mean pressure response and mean velocity response. As you increase the number of constituents for the uniform mesh, you see that the solution, the response is converging, and converging for a smooth like manner that is it's known that the transient is formed by that. And the logic is, as you increase the number of constituents, a better picture of the internal structure of the flow is captured, and then more close to reality this response is. The surprising result here is that mesh 2, that is the non-uniform one, just with 10 constituents, also has roughly the same response of the most finer mesh, uniform mesh, the mesh 1 with 80 constituents, as you can see here. And the same happens for the velocity profile of the flow. As you can see here, again, there is pictures of snapshots at non-dimensional times. And for all of them, mesh 2 has actually the same response of the mesh 1 with 80 constituents. So again, the internal structure of the flow is captured, and then the mean pressure and mean velocity are also captured. So the mesh 2 is capable of providing reliable transient response. And then as this mesh 2, the non-uniform one, applied a small number of constituents, less differential equations are solved, and then less computational time is required. And that is one of the main goals of the work. So we will analyze that further. So as I said, mesh 2 is enough to get precise and quite reasonable transient response. And like to assess the ability of the settlement, in other words, the use of the mesh 2 on providing accurate results, we will compare the response of this proposed model with the model of the two-dimensional model of Riaz et al. That applied the turbulence model K omega. And also we will compare the CPU computational time, taking as reference the numerical run carried out by Duan et al. That applied 2D 5-region turbulence model of Varden. As you can see here, for pressure, both are really near the experimental data of Homeboy and Hollywood, and the response of the proposal model in the 2D K omega model of Riaz is really near. And here we present the rate of energy dissipation along with the pipeline. And again, the proposal model is really near the response of the two-dimensional model of Riaz. That means the internal structure of the flow is really captured, is fairly captured, because like the dissipation is basically formed by, created by the internal forces that happens in the flow, that happens in the model between the structural shells that slide one each other. And computation is really efficient because, as you can see here, the model runs about 50 times faster than the model of Duan and get basically the same results. And Ryan compared his model with others found in the literature and found that is, for example, 300 times faster than the model proposed by Vardy Brown. In other words, it seems that the model can actually see the internal structure of the flow, provide fairly response for the mean values of the response, pressure, and mean velocity, and is quick. So I'm going to the conclusions right now. This work presented an steady friction model based on the theory of mixtures for describing turbulent transient flows, and the model is thermodynamically consistent, it's quick enough for real-time applications, and can see the internal structure of the flow. So it can be used for a large range of applications in the hydraulic analysis.